Okay, so following up after the plate tectonics chapter in the lab manual, we are continuing with uh, our study of minerals. So this is the beginning of the hand sample portion of this particular course. And I'll try my best to give proper instructions via recording. Since identifying hand samples in the following couple of weeks, minerals, igneous rocks, sedimentary rocks, metamorphic rocks, those are best done in person to have that face time and that hand feel with the individual samples themselves. Looking at videos and images can only get you so far in terms of learning them. But I digress. So the study of minerals. Minerals are relatively important in today's society. You see them pretty frequently everywhere. Um, so some examples would be what we have here in the upper left. We have what looks like a uh, makeup, possibly eyeshadow of some sort. We have table salt in the bottom left. We have non-dairy creamer in the top right, and of course we have baby powder in the bottom right. So what type of minerals are used for these items? We have kaolinite, which is almost like a very fine, powdery, soft mineral. It's very clay-like, it's very silky. So this is a primary ingredient in non-dairy creamer. We have talc in baby powder. We have muscovite, which is a very shiny mineral, and that can be ground up and used as eyeshadow to give us that very shiny eyeshadow look. And of course, we have halite, or otherwise known as salt, for of course table salt. So to define a mineral, there are 5 different requirements. And first and foremost, it has to be an inorganic material. Inorganic meaning it's not currently alive. Right? It's naturally occurring, so it occurs in the natural world. It's not something that is laboratory made. Of course, there are laboratory made compounds that are essentially the same arrangement of atoms and as a mineral. A mineral has to be solid, and there needs to be an orderly arrangement of these mineral atoms. That gives it a very specific shape, very specific characteristics that don't really break down. And of course, there's a definite chemical composition with these minerals. So the first and foremost property that's used to ID minerals is luster, color, cleavage, fracture, hardness, and streak. So these are all observational type of properties, right? Luster. What does it look like to us? Is it metallic or non-metallic? Color, what kind of colors are being exhibited? Cleavage and fractures. Whether we are looking at cleavage planes where the minerals is splitting along a definite crystalline plane, which is a plane of weakness, and that split will give us a very smooth surface that's almost reflective, or usually it's pretty reflective in the light. How many cleavage planes does it have, or if it's indeed a fracture, which is it doesn't break along any smooth surface, or when it breaks, it is not smooth, it's relatively rough and jagged. How hard is this material, is the mineral? If we take it and rub it up against glass or a nail, does the glass or nail scratch the mineral? Does the mineral scratch the glass? And what color streak does it have? What is the color of this mineral in its most powdered form? And this is done along a ceramic streak plate. So in the luster category, we can see that this has a very metallic luster. It looks very metal-like. And this, of course, has a very dull luster. This is doesn't have any shine whatsoever. We don't see anything that really stands out to us. It just looks like a yellowish greenish rock. And this has a very glassy, like luster. It's quite shiny and very glass-like. And of course now we go into cleavage planes and fractures, and this can get relatively complicated. This is usually where many students who are just starting to learn minerals have a very difficult time. So I'll try my best to outline this. If we go ahead and look at the first example, we have cleavage in one direction. So what we're looking at here is the mineral, what looks like a muscovite or a biotite. Oh, the example is muscovite. So muscovite has a single direction plane. So what it means is that there's a plane in a single direction. So we can see the edges here are relatively irregular. So there's no real definite shape to it. It's just drawn in kind of this oblong shape. But we can see that it breaks along this very flat plane, and it gives us a very shiny appearance to that breakage plane. All right. So in a one direction cleavage plane, we'll see that the mineral will sheet off in sheets. It'll kind of peel apart like a stack of papers. And in a two-directional cleavage, our example here is feldspar. So feldspar, they'll create a two-direction plane of cleavage. So we have a single plane of cleavage on here, at the top here, and any part of this plane that points up or towards the bottom is within that same plane. Right? So all the red that's being shown is a single plane of cleavage. And then all the green that I have shown here is now our second plane of cleavage. And all these different planes are exactly the same, and they're going to break along this vertical side. And this side right here, this odd shape, is not a plane of cleavage. This is known as a fracture. It's not really shown well here because it's drawn in such a way that it's very flat. So it's impossible to really tell. But if you look at an actual hand sample itself, you can see that there are going to be two shiny sides that create this brick kind of a shape in feldspar. And the ends of this brick it may have broken flat where it's kind of a plane, but it's not as shiny or reflective as the cleavage plane sides. And if we look at the cleavage plane of three directions, so example here is given as halite, we see that we have a very cubic-like shape. Right? And then we see this pattern repeating over several pieces or several different examples of the same cleavage planes. A common thing to look for when looking at cleavage planes or trying to identify cleavage planes is to look for a certain stair-step like pattern is what I tell my students, where we would see kind of the first step and it comes down again. That usually gives us a good indication of cleavage plane, and if you rotate that mineral, you should be able to draw again a stair-like pattern, and that would cover all the cleavage planes. So on the cartoon portion, we have very stair-like patterns. And we have, again, cleavage plane in two directions. We have the example of calcite. we notice here that we have a different angle. So cleavage planes don't exactly have to meet at 90 degrees. It could meet at about a 3120 degree. Right. But for our purposes, we'll just go ahead and call it 90 degree or not 90 degree. So in our lab, if you're working on this in lab, and for the midterm itself, we will be working with hydrochloric acid, which is a strong acid, but we've had diluted it to the point where it's safe enough. So hydrochloric acid fizzes with certain minerals, specifically with carbonates or calcite. You do want to test this on every mineral since we are not sure what mineral is exactly calcite. We have a streak plate. So this is going to be a white ceramic plate that we'll be using to grind the mineral against to see if we leave specific powder residue or a streak along the white ceramic plate. And we want to classify it based on color, what color is left behind. We have a glass plate and some general rules and instructions for using the glass plate as a scratch test is we want to place the glass plate on the flat of the table instead of holding it in our hand. In the event the glass plate shatters, we don't want glass to go into our hands. So certain minerals do have a taste to them, more specifically halite, so table salt. We do want to know that halite, salt, does taste salty. However, other minerals we want to be a little cautious of in terms of trying to taste, as some of them may not be good for us, especially if we've been putting droplets of acid on them. There are some special properties with minerals. They are not always 100% reliable, and these special properties would be, for example, the taste of a mineral, how magnetic a mineral is, or if the mineral reacts with acid. So first, how do we identify minerals? There will be 17 samples given in our lab, and we want to list out those samples in the left side. So we'll have that and just number them as so. First, we want to look at luster. What does that mineral look like? So we'll work our way from left to right. So we start off with the specimen number and we initially look at luster. What does the mineral look like? Is it glassy? Is it metallic? Is it non-metallic? So the first category is metallic versus non-metallic. Does it look like metal or does it look kind of like metal? Right? It doesn't have to exactly be shiny chrome like metal, but it could also just be more of a cast iron, not really shiny, but has that iron metal-y look to it. And that gives us a clear separation of our charts that we have in our lab manuals. Metal versus non-metallic minerals. Next would be color and streak. So these are the first observations that we should try to go for. What is the color of the mineral? What is the streak of it? Does it have a streak? Does it leave a powdery white streak, or does it just not leave a streak at all? So if it does not leave a streak, that means the mineral is harder than the ceramic plate. So if it's a light colored streak versus a dark colored streak. All right, what is the hardness of our mineral? Is it harder than glass, softer than glass, softer than the fingernail? The fingernail is about a 2 to 3 hardness, so it's relatively soft. But there are certain minerals that are softer than a fingernail. For example, one would be talc. So what's used in baby powder. Finally, we want to look at the amount of cleavage planes, or lack of if it's a fracture. And that's something that we would very carefully look at the mineral and look for that stair-like pattern, or parallel planes is usually a good way of determining cleavage planes. Also, what's shown here is we want to see if those planes form 90 degrees or if they form 75 or not 90 degrees. And finally, after we have determined the luster, the hardness, the color, the streak, the amount of cleavage planes or lack of, and other properties, so the other properties would be the special properties, we can finally narrow this down to the actual name of our mineral. And we will go ahead and ignore the economical use. And of course, we'll end the lecture on an internet meme. However, to state, yes, I do agree, this is a very nice cleavage. We can see these very prominent planes that will occur inside of here. So if you were to break off this piece, I would suspect that cleavage plane would look such as this. Right, so I'll go ahead and just draw these cleavage planes in. Hopefully you can have a good imagination in terms of what that cleavage plane looks like. Right? And of course, this top portion is all a single cleavage plane. So if you're to imagine this as a cliffside where we'd have a little person standing here, we'd have this cliffside, the level, the ground that you're standing on is a single plane. The cliffside itself on one angle, on one side, is a cleavage plane, and then if we go off towards the edge to where I've drawn it in red, that would be another cleavage plane. And that is it for the minerals lecture. Hopefully this was clear enough.